Okay, so here we are with the test number 4 physics review. So this is chapter 7 and 8. And there are 5 basic topics that I want you to be ready for. So I'm not going to do this, I'm going to do it in a kind of a random order. So let's start with chapter 8. So let's say first thing is going to be equilibrium. And so remember, equilibrium says that the sum of the forces in the x direction equals 0. The sum of the forces in the y direction equals 0. And the sum of the forces in sum of the torques equals 0. Now this little 0 here just means it's around some point. So we looked at a couple of problems like this in class. We had the one where we had a horizontal beam and there were two supports. And then we had it loaded with certain forces. Now these forces are due to the weight of the beam and the weights that are on top of the beam. And what we did was we summed the torques around either this point or around this point. And then we measured, say we're summing the torques around this point, we measure the distances from that point to the different forces. In this case we have 3 forces here and 1 force there. This force F1 doesn't create any torque because there's no moment arm. But these 4 do, and these 3 create clockwise torques, and this one creates a counterclockwise torque. So this one's supporting all these 3 torques, basically. And so you would, let's just give them some letters here. You can, we did quite a few of these in class, so I'm not going to go through the details. You can look back, and let's say this is distance here is x4. So what you would do, this is just to remind you, the sum of the forces in the y direction, you're going to have F1 and F2 going up, and let's call this, we'll call this W sub A, and we'll call this W sub B, and this W sub C. So those are the 3 forces. We did more than that in our lab. But you'd have minus W sub A, minus W sub B, minus W sub C. So that's the sum of the forces in the y direction. The sum of the forces in the x direction, there aren't any. And then you have the sum of the torques around this point, which we'll call that point 0. And so what you do is you take the forces, which are the weights, and you multiply it by the distances. So W sub A has distance x1, and then you think about if is this turning clockwise or counterclockwise. So it's counterclockwise, clockwise, so it's negative. And the same for the second one. So that'd be x2 distance times W sub B minus, then you take the x3 distance, multiply it by W sub C, and then you'd have plus for this one because that would cause it to go counterclockwise. So that would be plus x4 times F2. And that equals 0 also. So the way it works is you solve this, the torque equation for F2, and then once you have F2, you can plug that in there, solve for F1, given that you know where the weights are and the dimensions are. So that's kind of the procedure. Remember, clockwise is negative torque, and counterclockwise is positive torque. Just get your signs right and think about Yeah, that's the main thing, and make sure you match up the correct weight. So that could be one. We also did another kind of problem. So it's going to be one of these two kinds of problems. And we did this one in class as well. I think you had some examples at homework where you have a beam and there's some kind of a wall that we attach this thing to. And then there's a cable that goes somewhere. I should probably use something that gives me a straighter line here. So let's do that. So you've got this support, and then you've got the weight of the beam, and then you might have some masses here, and then you've got support force R sub x, support force R sub y, and you have some tension in the cable, and this might be W sub A, and this might be W sub C, and W sub B is the weight of the beam. And again, you're going to have to be given this angle theta, and you're going to have to know what these distances are. And we're going to sum the torques around this point. So we'll call that x sub A. We'll call that x sub B. We call this x sub T for tension, and you can call this x sub C. So those are the distances from this point. And so if you formulate the problem, when you have this cable that's at an angle, then you have to worry about x components. So the sum of the forces in the x direction are 0, but what you'll have is you'll have R sub x, which is pointing to the right, and you'll have the x component of the tension in this cable pointing to the left. So that's the x direction. So it's a little more complicated than the previous one. Again, because it's equilibrium, the sum of the forces in the y equals 0. So you have the support force here, R sub y. I'm assuming it's going up. If I guessed wrong, then I would get a negative answer. Then you have minus W sub A, minus W sub B, plus the y component of the tension, minus W sub C. So that's the y direction. And then you have the sum of the torques around some point, and that's also 0. So we're doing it around this point. So both of these unknown forces don't come into this equation. Now remember the tension here consists of two parts, T sub y and T sub x. So the way you would do this is you don't worry about T sub x because that's going through this moment arm. So you just start here and start going to the right. So you got this weight. This weight is going to have a force going down, which is going to cause this thing to rotate clockwise. So you have minus x sub A, W sub A. And then you'd have the weight of the beam, which also causes this thing to go counterclockwise. So then clockwise. So that's negative. Then the T sub y is going to be positive because this force would cause it to rotate counterclockwise. So you'd have x sub c times T sub y, and then you'd have this weight, the third weight, or the second weight. Third weight's the weight of the beam. So that's going to be negative because it's going to cause this thing to rotate counterclockwise, clockwise, which is negative. So then you'd have x sub c times W sub c. And the only unknown is this thing, T sub y. So once you have T sub y, then you can plug that in here and calculate R sub y. Now to calculate these values, you have this relationship that says that the tangent of theta, which is the angle that this cable is pointing at, is equal to T sub y over T sub x. So you can see if I know theta and I calculate T sub y from here, then I can calculate T sub x. So that's how those problems work. So again, look over what we did in class, make sure you understand it. I want you to, in both these problems, you want to be explicit enough that I know that you're not just copying down something without really knowing what you're doing. So it has to make some sense to me, that you explaining it well to me. Okay, so that's the first problem. Then you have the non-equilibrium situations. So there, what we dealt with were rotating disks. So one case that we looked at was this, where we had some weight hanging down, and that weight causes this thing to rotate clockwise. And what we did was we looked at the sum of the torques on the disk. So the sum of the torques on the disk, I'm going to use D there, is equal to alpha times the moment of inertia of the disk. Alpha is the angular acceleration of the disk, and that's equal to this torque, which is, there's going to be a tension in this cable, which we're going to call the capital T. So if I draw a free body diagram of this disk, you're going to have the tension in the cable, and you're going to have, that's it. So there's only one torque. Now we did look in class, we had the case where there was two tensions, where there was a cable. This went over a pulley in it, so you had both of them. But in this case, let's just look at the one with one tension. So the torque is, remember, torque is the radius at which the force is applied times the value of the force, which in this case is the tension. And because this thing would cause it to rotate clockwise, which is negative, we put a negative sign there. So it would be negative R, which is the radius of the disk, times the tension. Now if you had a weight on both sides, then you'd have one that would cause, this one would cause a clockwise rotation, the one on the other side by itself would cause a counterclockwise rotation. So one would be a positive torque, the one that goes this way, and the one that causes it to go that way is a negative torque. And you'd have a T1 and a T2. Now as far as, you could do some of the forces here, but that really doesn't affect the interaction between these two. So the only other thing we would do is do the sum of the forces in the y direction for this mass, this hanging mass. So you're going to have the tension pulling up, and you're going to have the weight hanging down, which, remember, weight is the mass times acceleration due to gravity. So for some of the forces, because this thing is moving up and down, it's going to be the mass of the this thing times the linear acceleration, and that is going to be equal to the sum of the forces in the y direction. So you have, if you define y going up, then it's going to be, tension is going to be pulling up and the weight is pulling down. So this tension is how these two things are connected, as well as the fact that there's some relationship between angular acceleration and linear acceleration. This one's linearly accelerating, this one's angularly accelerating. So it's A is equal to alpha R. Now you have to determine whether these have the same sign or not. So this thing falling down is going to be negative in the negative y direction. So we're going to get a negative acceleration associated with this hanging mass, which is going to cause this thing to rotate clockwise, which is negative. So a negative falling, a negative movement in the hanging weight is going to result in a negative acceleration, so they have the same sign. So in this case, we don't need a negative sign in there. And so those are the equations that you deal with in this case. If you had two masses, what would happen? You'd have plus r times t, and there'd be say this is T2 and this is W2, and then you'd have a thing hanging over here, and you'd have W1 and T1. So you'd add T1 here, and you'd have another equation. So you'd have a similar equation to this, but involving T1 instead of T2. The only other thing to think about is what if there was a pulley like we did in class, where the pulley's not as big as the disk. Well, in that case, what happens is that you have like a R pulley and an R of the disk. So this R here would be the R of the pulley, because that's the distance that the force is acting to cause this thing to rotate. One thing we did forget, was the moment of inertia of the disk. We need that as well, which is, for a disk, is 1/2 the mass of the disk. So this is the mass of the weight, mass of the disk times the radius of the disk squared. So the moment of inertia of the disk involves the radius of the disk. The pulley, will assume it's a massless pulley, and therefore it has no moment of inertia. So the radius of the pulley comes in here, whereas the radius of the disk comes in the calculation of the moment of inertia. Anyway, again, we did a couple of problems in class like that, so I'm not going to go through a specific one, just understand it. If you understand how this thing works, then I think you've got a pretty good idea of the whole rotating situations, because you've got torques, you've got a relationship between linear and angular properties, you've got calculating moment of inertia, you've got calculating torques. So it kind of handles, it's a fairly complicated problem, but I think if you study it enough, you'll understand what's going on. Okay, and then the final thing out of chapter 8 is conservation of angular momentum. We did a problem like this in class with the people going to the union meeting, and what we said was that if there are no external forces or no external torques applied, that the angular momentum remains constant, and the angular momentum is the product of the moment of inertia times the angular velocity. So this is the initial angular momentum, and if you have the final moment of inertia times the final angular velocity, that's conservation of angular momentum. And typically what happens in these problems is the initial moment of inertia does not equal the final moment of inertia. How can that happen? Well, we had the space station example where people move from the outside to the inside, and so when they move to the inside, they reduce the moment of inertia of the entire thing. That would be one way. You can think of somebody ice skating. If you did a model of somebody, and they went from that to keeping their hands down. What's happened there is that, again, they're moving the mass. They're not changing the mass, they're changing the distribution of mass, so they're making closer. You could have a case where say people are ice skating and they're connected by some rope, and they are spinning around each other like this, and then they pull themselves closer to the center. So again, the forces are occurring between these two people. There's no external forces. So in that case, as these people pull closer to each other, then they would spin faster here, or if they went the other direction, they'd spin slower. And it's all related to the difference in the moments of inertia. And that typically requires them to be, it's hard to treat these as disks, because a disk is usually fixed. So if you treat them as point masses, so in these moment of inertia problems, the point masses, the moment of inertia of a point mass is equal to just the mass times the radius squared. So typically the masses are not changing. What you're doing is you're changing the radius that's involved in the moment of inertia calculation. So you'd have some initial R and some final R. And then you can, I have to give you enough information here to solve for either an unknown angular velocity, an unknown radius, an unknown mass. Each one of those are possibilities. And the thing too is if you've got some kind of thing that's rotating, you've got a mass m1 here, and you've got a big mass m2 here, and they're rotating around some center point. The total moment of inertia, in this case, let's say this is r. This distance is r to the center. This is just some same distance to the outside. So the total moment of inertia is going to be m1r squared plus m2r squared. So you just add the point masses together, the moment of inertia, each one, to give you the total moment of inertia. So again, we did a problem like that in class. Think about it, just everything you need to know. Well, if there was a disk involved, then the formula for a disk is 1/2 mr squared, which you actually had to use in the previous kind of problem. Okay, constant angular velocity. We had a whole bunch of problems that we worked. Angular acceleration, sorry. Constant angular acceleration. So we looked at a lot of those. And basically, we're dealing with these variables. We're dealing with delta theta. We're dealing with omega 0, alpha, and t. And we have the four equations. I'm gonna, four equations. I'm gonna let you write those out. Find them. And basically, you're given 3 out of 5. 3 of these, and you can calculate the remaining 2 out of 5, whatever those are. One thing is you need to know how to convert from revolutions to radians, because all these involve radians. This is radians, this is radians per second, this is radians per second squared. So I might give you information in either revolutions per minute, revolutions per second. Convert from revolutions to radians or the other way, and also be able to convert from revolutions per minute to radians per second, and vice versa. You can look that up in your notes. Vice versa. Now, once you've converted to radians or radians per second, then you use the appropriate equations. So we've got a lot of practice with that. And then the final thing is satellites or moons. So this has to do with rotating motion but, or I guess it could be planets too. So satellites orbit around planets, they can orbit around moons, planets can orbit around the sun. Okay. And what we said in this particular case was that the centripetal force had to equal the gravitational force. And the centripetal force is equal to the mass times the centripetal acceleration. And the centripetal acceleration is either equal to v squared over r, which is, this is the tangential velocity, or it's equal to omega squared r, where this is the angular velocity, this is the tangential velocity. So what you have is you have some planet, and then there's some satellite out here, some distance r, and it's moving at some tangential velocity, and it's also rotating at an omega. So this is your tangential velocity, that's meters per second. Your angular velocity, which is radians per second. The radius, which is in meters. And so so that's centripetal acceleration. And this applies not just to things rotating, but it, things going around corners. If you're driving a car that's going around a corner with a certain radius and it has a certain velocity, then you need a certain amount of centripetal acceleration provided by the tires on the pavement to keep you going in a circle. If you don't have that, you just keep going straight. So to keep things in circular motion, you have to have this centripetal acceleration. Here, the centripetal acceleration is provided by the friction force between the tires and the car. Here, it's by gravitational attraction. If I had a string, here's somebody has a string and a ball, and you're taking the ball and making it go in a circle. Here, the force is this actual physical tension in the cable. So those are all three the same kind of thing. The centripetal acceleration and the corresponding centripetal force are related through these expressions. Remember how we derived that was we looked at circular motion and drew vector diagrams for both the change in angle and the change in velocity. And we said they had similar triangles, and we set them equal to each other. This is the ratios, the appropriate ratios, since they're similar triangles. And we were able to come up with an expression which says that the centripetal acceleration is v tangential squared over r. Okay, back to here. So that's the centripetal acceleration. Then you have the gravitational attraction between two bodies, and that's equal to the universal gravitational constant times the mass of the object, of one of the objects. So I'm going to say this is the mass. The mass that I used here was the mass of the thing maintaining circular motion. This is the big thing in the middle. So I'm going to use a big M for that. This is big M. This is little m. So you take the product of those two masses, the small mass that's rotating, and the big mass, which is holding it in orbit. And then you divide by r squared, which is the distance from the center of the big mass to the center of the little mass. So that's gravitational attraction. Remember, G is equal to 6.67 times 10 to the minus 11th, and the units are newtons meters squared per kilogram squared. How did I do that? Newtons meters squared, or kilograms meters, newtons meters squared divided by kilograms squared. So that's G. Write that on your paper. And so if you set these two things equal to each other, you have mv tangential squared over r, which is the centripetal force, is equal to the gravitational force, G little m big M over r squared. So if I cancel out the little m's because they're both on both sides, and solve for v tangential squared, this will go up to the top with g big M divided by r. So this is r squared down here. Almost lost that. So r squared. So you get this up here. R divided by r squared is 1 over r. Or the tangential velocity is equal to the square root of g big M over r. So one thing is that this small mass has no impact on what radius things rotate at, what speed they rotate at. So you don't need to know the mass of the satellite or the mass of the moon, whatever thing that's revolving, rotating. So, you can use this to calculate the needed tangential velocity given the mass of the moon, the sun, whatever's the planet, whatever this thing's rotating around, the satellite, the radius. Remember, r is going to be equal to the radius of the big mass. So this is the radius of whatever this is plus the height. So sometimes I'll give you this value, but sometimes I'll give you this and this, and you have to add them together to get the orbital radius. That's the distance from the center of this object to the center of that object. So make sure you use, if I give you a radius, make sure if it's not, if I say it's the elevation or height above the surface, that's h, which is not r. You're going to have to add the radius of the planet, which I'll give to you if you need it. I'll give it to you if you don't need it, but I'm going to give you the radius. I'll also give you the mass of the thing that it's rotating around. So, here I've solved for the tangential velocity. I could also, knowing the tangential velocity, I could calculate the mass. So it's, in this case, I've just chosen to use this form of it, but you can solve for the other variables if you want to. And then, so this will give you the gravitational force between two objects. This one will give you the velocities that something needs to travel at to to maintain a certain orbit at a certain radius around a certain planet mass. And the only other thing is, remember, there's this relationship between, say, here's the planet, this is the big M, and here's the little m, and if it goes in a circular orbit like this, and this is the radius, and this is the tangential velocity. So what we know is the time, we call it the period, which is the time to revolve. I always get revolve and rotate. Revolve, I guess. Revolve around big M. So if you talk about the period of things going around, how do you calculate that? Well, if you remember, velocity is equal to the distance divided by the time. Well, the distance this thing has to travel is 2 pi times the radius. That's the circumference. And t is the time it takes. Okay, that's the not. So this t here is the period. This is the period. The time for. So you can see if I know the tangential velocity and I know the radius, I can calculate the period. So think about that. And so I may ask you to calculate the velocity I may ask you to calculate omega. Omega is equal to velocity divided by the radius. That's the relationship between angular and linear properties. So if you have the linear velocity, you can calculate the period. T is equal to 2 pi times the radius, which again, this is the radius of the revolution, not the radius of the planet, not the height above the planet, but the sum of the two. So that's what that radius is, and you divide by the velocity, and you get time. And typically it takes hours or days for satellites to rotate around planets. It takes a year for the Earth to rotate around the sun. So, but typically satellites are going to rotate in a matter of hours. Okay, so that's it. Let's kind of go back and just reiterate what we said here. So there'll be an equilibrium problem. It'll either be just a flat beam like that, or a flat beam with a cable holding it. We've gone through problems like that in class. Then there'll be some kind of rotating situation where you have a way of providing constant tension, which is usually a weight hanging. We did a lot of experiments in class doing that, and I've given you an idea here of what's involved. What you probably, either you understand what's going on or you learn it and write it down if you can't just memorize it. So you've got some kind of rotating situation, which involves the moment of inertia. Then you've got conservation of angular momentum. Angular momentum is moment of inertia times angular velocity. And typically what happens is, in these situations, the moment of inertia changes because we change how the mass is distributed in different scenarios. The moment of inertia of a point mass is just the mass times the radius. Make sure it's the radius, not the diameter, but the radius. So that radius is not this, here. Yeah, in like rotation of planets around the sun, the r is the distance from the sun to the planet. Here, the radius is halfway between the two. It's the distance from the center of rotation to out there. Okay. And I told you the moment of inertia of a disk is 1/2 mr squared. The moment of inertia of a sphere is 2/5 mr squared. We did a problem like that in class, so you can review that as well. Here are the constant angular acceleration problems. We did a lot of those in class. And then we had a satellite problem. We did a couple of those in class as well. So that's it.